Hello, everybody. Thank you for joining us today for our fourth quarter quarterly HMS webinar. In just a second, I'll turn it over to JPAC and Nathan Chrisman. JPAC is the post-fire debris and sediment expert on the HMS team, and Nathan is a hydraulic engineer out of the Kansas City district. Jay and Nathan teamed up on a hydrologic studies general investigation project to test and document new reservoir sediment routing options available in the HMS software. Their work is available on the HMS tutorials and guide space. And if you look in the chat area, there's a link to one of the tutorials there where you can data sets. Time will be dedicated to discussion and questions at the end of the webinar. Also, the webinar is being recorded and the video will be posted to our website soon. And then also everybody is on mute to minimize disruptions. Please type your questions in the chat and we'll answer them when we get to them, or either at the end of the webinar if there's enough time. Now I'm going to turn it over to Jay and Nathan for their presentation.
Okay, thank you, Matt. My name is Jay Pak. Today, I'm going to present about the new feature in HEC HMS we call Dynamic Reservoir Volume Reduction feature. And then Nathan Chrisman from the Kansas City district is going to present a 3-case study with this new Dynamic Reservoir Volume Reduction feature in HEC HMS. As you can see, left side figure, you can see the map, location of this 3 major case study. And the right-hand side, I took this picture around this April when I site visit for Ventura County. This material dam built in 1947 for water resource and flood control purpose. But right after 5 years, in 1952, it's pretty much filled. This one is maybe after 70 years. You can see behind this dam, it's kind of pretty much 100% filled and they're growing this vegetation. My ultimate goal with the HEC HMS, we want to simulate this situation. From the certain sediment yield from the upper watershed, even including burn condition, how much we can estimate the debris yield or sediment yield into the behind the dam. That's the goal. This feature funded by post-wildfire flood risk management funding, and then this case study for Nathan and me is funded by headquarters GIS funding. We really appreciate this funding support to generate this nice feature and then great case study. Through this presentation, I'm going to talk about why do we need this reservoir volume reduction feature. And then I'm going to talk about a little bit reservoir volume reduction physical process in HEC HMS. After that, Nathan is going to present his 3-case study with this new reservoir volume reduction feature. Okay, and then finally, we're going to have some time to get some feedback and comment. Okay, why do we need this? I have 2 main purposes. First one, I can explain with this small diagram. I got this picture from the Reservoir Sediment Handbook. As you can see here, horizontal axis is time. From the 1920 to the 2000, vertical is volume, sediment store, is reservoir storage volume. Okay, through the time, regular season, we have some sediment yield from the upper watershed into this reservoir, gradually reduce the storage capacity. But right after fire, you can see this rate is increased until fire factor disappear. Another normal season, and then reservoir capacity. Okay, so as you can see here, after reduce the certain capacity, they need some raised dam height, and then to recover their capacity back to original design capacity. So I want to simulate this situation through this long-term simulation with fire condition or without fire condition with the HEC HMS. That's the first goal. Second goal, you can see there's the heavy Excel spreadsheet. That's the normal way Kansas City District to simulated sediment yield to the reservoir, each reservoir, using this Excel spreadsheet. That is some kind of tedious kind of job, but we want to reduce this work and they replace with the HEC HMS. Okay, Nathan is going to present a little bit more about this. This one is a simple physical process in HEC HMS in terms of reservoir sediment deposition. So we released HEC HMS 4.0 with the first sediment capacity, even including watershed, subbasin, reservoir, and reach element. At that time, especially for reservoir element, we implemented the sediment trap efficiency with the CHEN method, but we didn't update it elevation storage and elevation area curve with based on the sediment deposition. We just kept some static relationship graph. And then we separately generate the sediment hypothetical tank and just calculate the cumulated sediment. But that is not enough for us. Now we updated our HEC HMS reservoir sediment capacity, especially for reservoir. We can update it each time step, elevation storage, elevation area curve based on the deposit amount. Then we can generate the more accurate sediment trap efficiency and then provide some overall long-term sediment yield amount. Okay. Top of that, we can provide the two options. So in terms of sediment pattern, we have something fine particle or coarse particle. Especially for fine particle, clay and silt normally deposit from the bottom of reservoir. We call the V-shaped deposit pattern. We just default for clay and silt, V-shape only. The mean is clay and silt deposit from the reservoir bottom. But for coarse particle like a sand and gravel, we can provide the two options. Especially for small reservoir, we can still choose the V-shape, deposit from the bottom for sand and gravel. But for long, large shape of reservoir, then you can choose some tapered, elongated tapered option. That means deposit from the upstream. Okay, that's the you can see from this graph. This one is a blue solid, green solid line. That is original storage elevation storage curve. But if we choose some V shape, that means is reduce the storage capacity from the bottom like that. But if we choose some elongated tapered option, it's gonna be reduced storage capacity from the top. So we can manage this one in terms of elevation storage curve with the deposit amount with the deposit pattern. Then we can update this elevation area, elevation storage curve each time step. That's the short kind of a background about this process. Or with that, we can provide the two options with the two different trap efficiency methods with this user interface. If you choose the CHEN trap efficiency method, you're gonna have this user interface. That's the simple. You need just average temperature, and then reservoir capacity option. Yes, then you're gonna have two pattern, deposit shape, V shape, or elongate tapered shape for your sand and gravel. Automatically clay and silt is selected for V shape. And then another option, BRUNE's trap efficiency method. We developed this new BRUNE's trap efficiency method for Kansas City District because Kansas City District using this trap efficiency method instead of a CHEN trap efficiency method. To use that, you need additional input parameter, annual inflow volume, capacity elevation and the two constant value. And then same, you need to choose the reservoir capacity option and then select deposition shape. Deposition shape, V shape or elongate tapered shape for your sand and gravel site. This one is a typical HEC HMS reservoir element user interface. Okay, a reservoir. You can choose some reservoir method, storage method. Also, you need to provide some elevation storage, elevation area curve like this. Normally, we can get this one from the measured data set. And then you can put some initial value for initial elevation. And then if you have some structure like a spillway, you can put some spray information. Also, you have something outlet structure like a curvet, you can also add that one. With that, HEC HMS generate output inside the result tab. In this case, you can see blue solid line in here. That's the elevation line. Elevation increase up to spillway and then steady. But before, with that steady elevation area, elevation storage curve is not changed. But now, based on the deposit amount, we can change is reduce the elevation area and elevation storage based on the deposit. That's the new result. And then also we can provide a separate result. This one is elevation storage curve. This one is elevation area curve through the time. This one is every month. But we cannot provide this one from the result tab. To find out this time series data, you need to go to HEC HMS DSS output. Open DSS output, you can choose this, the time series result from the DSS. Then you can generate this information through the time. And then another application. So this one is actually generated for post-wildfire condition. I choose this debris basin from the Los Angeles area. So this is called Brand Debris Basin. Okay, we simulated about 4 months after fire. So this one is elevation area curve. This one is elevation storage curve with multi-sequence debris prediction method. In the new version of HEC HMS, we can provide 5 different debris yield methods. Okay, this is one of them. And there's another method we call USGS emergency assessment. Then they can generate the different debris amount. Okay, with these two options, we generated these two results. For example, this one, elevation storage curve. You can see this one is a blue green line that is generated from November 30. And then the last one is a purple line is April 2nd, 2003. This is November 30, 2002. Almost kind of a 4 months difference. Through this one storm season, first one is we have about 135,000 cubic meter storage, but through the time, through the event, debris event, around April 2nd, we have only 55,000 cubic meter. The mean is almost 60% this debris basin capacity is reduced through the whole debris yield. Okay. With this information, normally after fire, especially around the Southern California area, many different debris basin is filled through the burn area sediment yield. Then in terms of emergency management purpose, we need to clean out right away because most of the debris basin design just for capturing one event. So maybe let's say 40 debris basin in a field through this fire event and storm event. Which debris basin we need to clean out first? We need to make some prioritize this clean out schedule. But if we have this kind of information with HEC HMS before clean out based on the forecasted or measured rainfall event, then we can easily prioritize cleanout schedule. And then also another one is if this is already filled with the kind of future forecasting, we're gonna have something huge rain tomorrow. Then based on that information, we can estimate how much debris yield and how much debris amount to overtop this debris basin and inundate it to the downstream community. Then we can have some great information to prepare the emergency evacuation plan also too. That is a kind of information we can generate it from this application. Okay. Also, we provided this new tool, but we have a limitation. I have this major limitation got from the Nathan 3 case study. So currently, we cannot provide it proper residence time, especially for fine particle with a long, large shape of reservoir. Okay. So even we built elevation area, elevation storage curve based on the measured data, survey data, but that is not enough to provide it something proper shape of reservoir, especially long shape. Okay, that case HEC HMS cannot provide accurate estimation. For example, we tested with this two case, Kanopolis Lake. Okay, this is kind of a long shape. Average width, I just measured from the area photo. Average width 1.13 kilometer. Average length about the 35.8 kilometer. And then I generate the simple shape factor, length divided width. That means it's about the 32. And then I compare the, without this shape factor. I just kind of quick and dirty simulation, just simply modifying this HEC HMS code with the shape factor. Okay, for example, this Kanopolis without shape factor, 60% trap efficiency. With this shape factor 32, and then 94% trap efficiency. Then we can compare with the measured USGS trap efficiency 95, pretty close. Another case study, Turtle Lake. Turtle Lake shape factor 8.5, and then without shape factor 57% trap efficiency, and with shape factor 96% trap efficiency. That is pretty close to USGS measured trap efficiency 98. So we needed this kind of feature in the future. So I'm looking for some funding. That's why I'm prepared some GI funding for next FY23 GI funding to implement this new feature. So we'll find some way to implement this one. Then we can improve a lot. With this limited situation, Nathan, he changed in terms of calibration. Based on we generated some gradation curve with 4 grain size, but we have limitation for this clay and silt. And then for calibration purpose, he changed some amount, fine particle amount, silt and clay, change it to the sand amount. Then we can properly calculate it, this case study better than without changing gradation curve. We can manage it some manually for gradation curve, but if we generate this one, then maybe we don't need that much changing measured gradation curve. So I think that's my last slide. I'm gonna turn it over to Nathan. Can you share your screen, Nathan?
Yep. Can you see my screen?
Not. Yes.
You can see it now? Okay. So hi, everybody. I'll be presenting on the 3 HMS models that we created to test the new reservoir volume reduction tool. And the 3 reservoirs that we created models for are named Tuttle Creek, Kanopolis, and Perry. And all 3 of these are located within the Kansas River watershed. 73,000 acre-feet. Since the dams were constructed, though, there's been quite a bit of sediment deposition within the lakes. Tuttle Creek has lost 46% of its original multi-purpose pool volume. KANOPOLIS has lost 36%, and Perry has lost 18%. And such a large amount of sediment deposition has negatively impacted the authorized purposes. For instance, at KANOPOLIS, sediment accumulation near the outflow gates has created difficulties in the operation of the gates, and that's required expensive dredging to remove the sediment. At Tuttle Creek, sedimentation has significantly reduced the surface area of the lake and made several of the boat ramps inaccessible. It's also reduced the volume available for water supply. And there hasn't been any sediment removal at Tuttle Creek, but that's something we're currently investigating. For the past 3 years, we've been analyzing all 3 of these lakes as part of the Kansas River Watershed Study, which is a planning study to estimate sedimentation and propose potential solutions for a total of 17 core and bureau lakes. For the watershed study, we used more manual methods for estimating sedimentation, using tools such as Excel and ArcGIS. And since the data from the Kansas River watershed study was already available, we reused it when creating the HMS models for this case study. The results from the watershed study showed that Tuttle Creek will have lost 93% of its original multi-purpose volume by the year 2124. KANOPOLIS will have lost 75%, and Perry 57%. And this figure on the right shows how the surface area and depths in Tuttle Creek will change in the future. And you can see that over time, the lake's area becomes significantly smaller. I'll be going over some of the methods that we used in the Kansas watershed study. Since we used some of the data in the HMS models, and the steps are pretty similar to what HMS uses. The first step was to create a sediment load rating curve using sediment concentration measurements collected upstream of the lakes. And most of that data was accessed from the USGS website. The graph on the right, it shows an example of one of the rating curves that we created for Tuttle Creek. The yellow and the blue circles are the concentration measurements, and the solid blue line is the rating curve we created. And the rating curve flattens out at the higher discharges, and that's something we observed at all the gauges. After we created the rating curves, we used them to calculate the daily sediment load from the daily flow rate. Then the next step was to determine the mass of sediment deposited based on the lake trapping efficiency. And for that, we used the BRUNE method, which is an empirical method for calculating trapping efficiency based on the lake volume and annual water inflow. Once we had the mass of sediment trapped, we converted it to volume using bulk density measurements that were collected at each of the lakes. The daily volume of sediment trapped was then summed over the study period to determine the total deposition. And we calibrated our methods by comparing the predicted volume change to the measured volume change, and then adjusting several of the parameters. Then we used the same methods to calculate the future without project volume change, which we then used to create updated elevation storage tables. To do that, though, we had to do quite a bit of Excel and GIS analysis to estimate at what elevation in the lake the sediment would deposit. And then finally, once we had the updated elevation storage tables, we then inputted them into a RES-SIM model for predicting downstream impacts. So those were the basic steps that we used in the Kansas watershed study, but there are several disadvantages with these methods. For one, the Excel spreadsheets we used were really large, and having such large spreadsheets made it difficult to track our work and created more opportunities for user error. And the screenshot on the bottom, it shows one of the examples of one of the spreadsheets. And you can see that there's many rows and columns. And the GIS data sets that we used were also large, and the methods were pretty labor intensive. So we created 3 HMS models to see if HMS could offer a better method of computing lake sedimentation. The HMS models were pretty simple since they only included 3 elements, an inflow element, a reservoir element, and an outflow element. And we didn't need any sub-basin elements since we were using time series data for our inflow. For the sediment inflow, we used the daily sediment loads that we'd calculated from the WATERSHED study. We also had to specify the incoming gradation for the load, and for that we used the USGS measurements that were collected upstream. For the reservoir element, we had 4 main parameters to enter. First was the initial elevation storage and elevation area tables, which were obtained from bathymetric surveys. For the lake trapping efficiency, we tested both the BRUNE and CHEN methods, but there wasn't a huge difference between the 2 results. For the deposition shape, we tested both the V-shape and elongated taper methods, and I'll talk more about those results later. And for outflow from the dam, we used a time series specified release, and that was obtained from water management records. We used a time step of 12 hours and a fairly long simulation period, up to 60 years for KANOPOLIS. So we compared the HMS results to the measured volume change that we computed from bathymetric surveys. The surveys have been collected approximately every 10 years using a variety of different survey methods. The older surveys were collected along fixed range lines using both boat and land-based methods, and the range lines were spaced fairly far apart, as this figure on the top shows. Recent surveys, though, have been collected at a denser spacing within the multipurpose pool, and LiDAR has been used to collect higher elevations of the lakes. And because there's difference in the survey methods, there are likely some errors in the measured volume change, and that should be kept in mind when comparing to the model results. And when we looked at the initial model results, we found that the model volume change was consistently lower than the measured data, and that the sediment was depositing at too low of elevation within the lake. As Jay discussed, we think the trapping efficiency is low because how HMS currently calculates the clay and silt trapping efficiency doesn't account for the lake shape. HMS just assumes that its length is equal to its width.
So,
how do you feel
gonna be
about
spoiled
that?
for options.
Yeah.
In reality, though, the lake's lengths are much greater than their widths, which significantly increases their trapping efficiency. As Jay mentioned, he's already investigated ways to correct for the shape of the lake, but he hasn't implemented anything in HMS yet. And this wasn't a problem for the sand sizes, since the program uses either the BRUNE or CHEN methods for sand. The large size of the lakes also appeared to be what was causing the sediment to deposit too low in the lake, since the clay and silt sediments don't strictly follow the idealized V-shaped method. After seeing the initial results, we found that we could calibrate the models by shifting most of the clay and silt sediment into the sand grain class. And the amount we had to shift was unrealistic based on measured gradation, but it allowed us to account for the lake's shape and size. At Tuttle Creek, the final gradation we used was 5% clay and 95% sand. We also had to lower the default specific weight that HMS uses for clay and sand to account for the shift in gradation and the lower clay trapping efficiency. We decreased clay specific weight so the volume of clay deposition would equal the clay deposition with the correct trapping efficiency. And we decreased the sand specific weight to near the average of the bulk density measurements. It differed somewhat from the measurements because of the 5% that was still clay, and because we deviated from the measurement slightly to better calibrate the model. And this plot on the right, it shows the results from the Tuttle Creek calibration. On the left axis is the measured volume, is the volume change, and on the bottom axis is the elevation within the reservoir. The solid lines are the measured volume change, while the dashed lines are the HMS results, and the vertical black line is the multi-purpose elevation, which is the elevation that we were most concerned about for the purposes of our study. And the reason the measured volume change for the 2020 survey only goes up to the multi-purpose elevation is that we weren't able to collect data any higher. And overall, the model results matched pretty well with the observed volume change, especially at the multi-purpose elevation. The main outlier in the HMS results is the 1983 survey, which doesn't show enough deposition in the model. But as I mentioned earlier, the survey data itself might not be right. And the measured data for the 2000 survey is also probably an error, since it doesn't look realistic compared to the other surveys. And then also in the middle elevation reservoirs, the observed volume change is typically higher than the modeled volume change, and that could be because we were only able to use a single bulk density value in those areas. And we followed the same methodology we used for Tuttle Creek when calibrating the KANOPOLIS model, but we ended up using slightly more clay in the final gradation for KANOPOLIS, since the measured data showed more deposition at lower elevations. And that can be seen in this plot, where the deposition is steeper at the lowest elevation, but then flattens out some. And I think that's caused by KANOPOLIS being much smaller than Tuttle Creek. And we ended up using 10% clay and 90% sand to count for that. And overall, the HMS results matched pretty well with the measured data. And this figure is just for the older rangeline surveys. And the observed and the model data sets match pretty well for the first and the third time periods. But there's definitely some errors in this area where I circled in red. The second survey period, it shows less deposition in the model, and it actually shows that the deposition decreased from 1982 to 1993, and that's not really physically possible. So either the 82 or the 93 survey are in error. And this figure is for the model and observed volume change from the two newer surveys. And it also matches pretty well. We didn't have any data for the higher elevations of the lake, since we used LiDAR in these newer surveys, and the water surface was different on the days they collected the LiDAR, and that made the results unreliable. For the Perry Lake calibration, we used 9% clay and 91% sand for the incoming gradation, and that's between the Perry and the Tuttle Creek models. The figure on the left shows the volume change for the older surveys, while the figure on the right shows the volume change for the newer surveys. And the model under predicted volume change for the first survey, but matches better for the final two surveys on this figure. It also under predicted deposition in the middle elevations of the lake, like it did for Tuttle Creek. But since we were most concerned about the multi-purpose elevation, this wouldn't affect the results of our study much. And then we also looked into how well the modeled pool elevation compared to the observed pool elevation. And this figure shows the modeled and measured pool elevations at Tuttle Creek. And it shows a pretty good agreement between the two. The blue line is the modeled data, the orange line is the measured data, and the dashed gray line is a model run without including any sediment. And you can see that they match up pretty well. Over time, the gray line begins to diverge from the other results, and that's because it's not taking into account the reduction in volume in the lake. And at the end of the simulation, without including sediment, the model's 9 feet too low, while it's just 1 feet high when we did include sediment. Then we also compared the HMS results to results from a RAS sediment model that we created for Tuttle Creek. The RAS model was a 1D quasi-unsteady sediment model that we calibrated to the 2000 to 2020 survey period. And we used the same sediment loads for inputs into RAS that we'd used in HMS. We simulated both models over the future without project period, which goes from the years 2024 to 2124. And this figure on the right, it shows the cumulative volume change over the whole simulation. Gray is the HMS model results, and blue is the RAS results. And you can see at most elevations, the two match pretty well. And there's some deviations at the higher elevations where RAS deposits more sediment. But overall, the two match well, which is important since RAS is a more established sediment modeling software. So after comparing all the results, we thought that overall HMS performed well based on how well it matched both the observed data and the RAS results. If we had to redo the Kansas watershed study, we would probably use HMS for most of the analysis. And it will also probably be useful for any future studies we may work on. There are a few limitations that I thought would be good to mention though. First, HMS doesn't explicitly account for the sediment consolidation, which is where fine sediment gradually becomes denser over time. We somewhat accounted for that by calibrating the density values to the measured data, but not simulating sediment consolidation may introduce errors for the future without project runs. However, that's a limitation in our spreadsheet method and the RAS model as well. A second limitation is that HMS can't give you the longitudinal volume change like RAS can, since it doesn't include any cross-section data. And that would be important if you were interested in how fast the delta in the lake would progress downstream over time. Also, right now, HMS can't give you as an exact calibration as RAS can. Another limitation is that HMS currently can't simulate sediment removal methods such as drawdown flushing, though this could be an area of future improvement in the model. There were some limitations in the calibration methods that we used, since they required quite a bit of measured data in order to calibrate the model. That amount of data likely won't be available for many lakes. And as I mentioned before, there's quite a bit of uncertainty in the measured data that we did have. And we only tested our methods at 3 lakes, so further testing might be needed to make sure the method works for other types of reservoirs. Despite its limitations, HMS offered several great advantages compared to other methods. First, it eliminated the need to use the large Excel spreadsheets and labor-intensive GIS methods we used in the Kansas watershed study. And that likely decreased the chances for user error, since most of the calculations are done internally by the program. Another advantage of HMS modeling is that it was pretty easy to set up and calibrate. Now that we have the process down, it would probably only take a day or two of labor to create and calibrate the model. And the models also ran pretty quickly, with run times of around 1 to 2 minutes. So in conclusion, we tested the new reservoir volume reduction tool on 3 reservoirs in the Kansas River watershed. After calibration, we were generally able to accurately predict volume change compared to the survey data. There are some discrepancies, but many of those can likely be explained by survey errors. The HMS tool offered improved efficiency and organization over methods we'd used previously for the watershed study. And finally, the HMS results compared well with a RAS 1D sediment model, which is a more established. That's everything I had.